In this video, we're going to explore the amount of possible work we could harness from a standard battery. So the modern alkali batteries help us solve several problems that early batteries could have, especially our voltaic cell design. When we think of our voltaic cell, the problem with voltaic cell is that it is concentration based. As one of your solutions starts to deplete, as say copper starts attaching and you run out of copper in solution, there's just less ions attempting to attach to the copper. This just means there's less opportunities for electrons to move through the wire and reduce the copper. As a result, there's just less electron flow. Additionally, the more zincs that you actually build up, even though it's rare, every once in a while when the zinc ion does impact the zinc bar, it can acquire electrons, and it can pull electrons in the opposite direction. This is non-spontaneous, it's disfavored, but it can randomly occur. And with enough zinc in solution, this propensity to have electrons flow in the reverse direction starts to get greater. It's still not particularly common, but times greater concentration of ions means more per second could occur. So we're losing our favorability to go towards the copper as we run out of copper, and we're increasing the chance that something goes towards the zinc. Eventually, this cell stops working. The voltage actually decreases while it operates. The difference in concentrations affects the voltage. This is a problem, and concentration-based batteries, as a result, are not ideal. This is where the modern alkali battery comes in. It is zinc and manganese dioxide. So we have a zinc solid plus 2 hydroxide goes to zinc oxide plus water plus 2 electrons. Additionally, we have manganese dioxide solid plus 2 waters plus 2 electrons going to form manganese hydroxide and 2 hydroxides. These are made up of solids in both the reduced and the oxidized form. And a solid's concentration doesn't change, unlike an aqueous solution. Our hydroxide concentration is maintained for every 2 electrons transferred. So this reaction doesn't have the concentrations of its electrolytes altering. This means that it maintains a consistent voltage throughout. It doesn't weaken as it consumes the materials and produces more of one side or the other. This is fantastic. It means our flashlights don't dim the longer you use them. If you remember really old flashlights and old batteries, or you see them in movies, brand new lights would be brighter. As they got used more and more, they'd get dimmer and dimmer. That tends not to happen very much anymore. They are consistent through till nearly the end. In our case, though, let's find our max possible work. Let's find the free energy, in this case, for a AA battery. Knowing that the voltage doesn't change simplifies our calculation. We don't need to take it in infinitesimally small steps to look at how the concentration changes and therefore the voltage changes at every single electron transfer and then calculate out how much free energy for that single electron transfer over and over and over. Instead, we can just assume it's the correct voltage the entire time. Our free energy, remember, is equal to the negative mole of electrons, Faraday constant, E cell. Now, while these redox and oxidation reactions aren't available in the back of our book exactly, I can tell you that the voltage for these two is 1.5 volts. So we know the voltage, Faraday's a constant, moles of electrons. For a single AA battery, how many moles of electrons are we going to move? Well, for a standard AA battery, there's approximately 2.4 grams of zinc and 6.5 grams of NnO2. If we look up above, we already have our electrons balanced here. So for every 1 MnO2, we need 1 zinc. We actually figure out if one of these is a limiting reagent or if they're fairly close inside a battery to begin with. But we can actually figure out, but assuming that all of one of them reacts, whichever is the limiting reagent, we can calculate out the number of moles of electrons that must be involved. So really quickly, we need to figure out which of these is limiting. 2.4 grams of zinc at 65.38 grams per mole, and 6.5 grams of MnO2 at 86.94 grams in 1 mole gives us 0.0367 mole of zinc and 0.0747 mole of MnO2. So we say our limiting reagent here is our zinc. If it was 1-to-1 the balance reaction, we have less zinc. So that is the most material that can possibly react. And since each zinc gives us 2 electrons, the maximum electrons that we could have this battery transfer is 0.0734 mole of electrons. So we provided the voltage for a standard AA battery. We're able, with some information about the makeup of a battery, to determine the moles of electrons. What's the maximum work a AA battery can give us? Well, that Gibbs energy is going to be equal to negative 0.0734 mole of electron, 96,485 joules per mole electrons volt, and 1.5 volts. Gives us negative 10,625 joules, or the Gibbs energy available from a AA battery is negative 10.6 kilojoules. 10.6 kilojoules seems a reasonable amount of energy at first. Remember, something like a 100-watt light bulb uses 100 joules per second. And so if we have 10,600-ish joules, and we use 100 of them in 1 second, then you could run a standard 100-watt light bulb for 106 seconds, or just under 2 minutes. If you have a 100-watt light bulb around your home, think about how long it's been running for. How many batteries you would have had to swap out and use constantly to power it. Battery sources for electrical power are useful, but they're resource intensive and very wasteful if they're not rechargeable.